Today, we're jumping into one of the most exciting races in tech history. And now, it's not about runners on a track, it's about ideas in a lab. We're going to follow the baton of innovation as it gets passed from one groundbreaking AI model to the next, tracing the incredible story of how machines learn to see.
So here's our game plan. First, we'll hit the starting line with the model that changed everything, AlexNet. Then, we'll watch the intense mid-race battle between VGG and GoogLeNet. After that, we'll see how ResNet smashed through a wall to go deeper than ever before. And finally, we'll talk about how you can actually use these champion models today before wrapping up with a quick Q&A to lock it all in.
But before we start the clock, let's just pause on the big question that started this whole revolution. How do you teach a machine to look at a picture and see a cat, not just a bunch of pixels? How do you get it to see the world like we do? That's the challenge.
And we're off. The year is 2012. The first runner, AlexNet, grabs the baton and just blows past everyone. This is the moment that proved deep learning wasn't just hype, it was the future of computer vision.
You have to understand, before this, progress was slow. People were handcrafting features, trying to tell computers what to look for. Then AlexNet comes along and doesn't just win the biggest competition of the year, it absolutely demolishes it. A 15.3% error rate was a nearly 10-point drop from second place. That's not a step forward, it's a quantum leap. This was the moment everyone realized a deep network could learn its own features way better than we could teach it.
So what was the secret sauce? Well, it was a mix of brute force and pure genius. They used this clever hack to split the model across 2 GPUs, which let them train it in less than a week, totally unheard of at the time. But the real game changer was using something called the ReLU activation function. Think of it like a light switch. Older networks had dimmer switches that could get stuck in the off position, but ReLU was a simple on-off switch that let information flow freely and kept the learning signal from dying out. AlexNet didn't just win, it lit up the entire racetrack for everyone else.
Okay, baton passed. By 2014, the race was all about one thing, depth. AlexNet proved that deeper was better, so now the question was, how deep can we go? 2 new teams, VGG and GoogLeNet, came up with wildly different answers.
And their philosophies couldn't be more different. On one side, you have VGGNet, which went for sheer brute force. Its strategy was basically, let's just stack a whole bunch of simple, identical layers on top of each other and see what happens. Simple, elegant, but man, it was a beast, with over 138 million parameters. On the other side, you have GoogLeNet, with its Inception module. This was the work smarter, not harder approach. It acted like a team of specialists looking at the image at different zoom levels all at once, while using clever tricks to stay incredibly lean and efficient. And in 2014, smarter won.
But here's the thing. As these networks got deeper and deeper, they hit a wall. A really frustrating wall. All of a sudden, adding more layers started to make the models worse. Something was fundamentally broken, and the next runner in our race was going to have to smash right through that barrier.
And that wall has a name, the vanishing gradient problem. The best way to think about it is like that game of telephone. You whisper a message at the front of a really long line. By the time that message gets to the person at the very back, it's just a garbled mess, right? That's exactly what was happening here. The learning signal that gets sent from the end of the network back to the beginning was fading to practically nothing. The network was just too deep for the message to get through.
This was the million-dollar question. If depth is the key to power, but also the very thing that's stopping you, what do? How do you get around this? This is the exact problem that the next model, ResNet, was built to solve.
And the solution, the one that won the whole thing in 2015, was just beautifully simple. Instead of forcing that message to go down the long, winding road, you just give it an express lane, a shortcut.
This slide shows the genius of it. Look at the left, that's the old way. The learning signal has to fight its way through every single layer, every single roadblock. But on the right, you see ResNet's idea. See that little arc going over the top? That's a skip connection. It's an express lane that lets the original information and, crucially, the gradient just bypass all the roadblocks and flow straight through. This one simple idea unlocked the ability to train networks that were over 150 layers deep. It was a total game changer. So now we have these incredibly powerful, super deep networks. And the best part is, we don't have to build them from scratch every single time. We can actually stand on the shoulders of these giants. And we do that using something called transfer learning. Think about it. A model that's been trained on millions of images from the internet already knows how to recognize basic stuff, right?
edges, corners, textures, colors, the building blocks of vision? Transfer learning lets us take all that pre-baked knowledge and just fine-tune it for our own specific task, even if we don't have a whole lot of data.
But what if even one of these giant expert models isn't enough? Well, to get the absolute best results, sometimes you don't want a single expert. You want a whole committee of them.
This is the core idea behind ensemble models, specifically a technique called stacking. You basically train a few different models to do the same task. They're your first-level experts. Then you take all of their predictions and feed them into a brand new second-level model. This final model's only job is to learn from the committee and make the final call. It's like having a panel of experts weigh in before making a super-informed decision.
All right, we've crossed the finish line of our race, so let's do a quick cool-down lap with a few questions to make sure we've really nailed down the lessons from each stage of this journey.
Okay, first up, let's rewind. Think back to our pioneers, AlexNet and VGGNet. What was their claim to fame?
Okay, so for AlexNet, the big innovation was using multiple GPUs. It was a hardware hack that proved more compute power was a huge part of the answer. VGGNet, on the other hand, was all about that methodical, simple approach to depth, just stacking tons of small 3x3 filters. And the reason VGG was so huge, it was those massive, fully connected layers at the very end of the network.
All right, next up, the innovators. What was GoogLeNet's secret weapon for efficiency, and what was that brilliantly simple trick that ResNet used to go deeper than anybody thought possible?
So GoogleNet's secret was the Inception module, which used these clever one-by-one convolutions to shrink down the amount of data before doing all the heavy processing. Super efficient. And ResNet, its magic trick was the residual connection. Don't let the math h of x equals f of x plus x fool you. All that's saying is you take the result of your layers, f of x, and you just add the original input, x, right back to it. That simple addition created the express lane we talked about. It's that simple, but it changed everything.
And for our last lap, let's talk about actually using these models. When is transfer learning a good idea? And why does a committee of models almost always beat a single expert? Right, so transfer learning is your best friend when your own dataset is pretty small. The trick is to freeze the early layers of the pre-trained model, the ones that learned about edges and colors, and only retrain the final few layers on your specific problem. And ensembles, they work because of the wisdom of the crowd. Every model makes mistakes, but they all make different mistakes. When you average their predictions, those random errors tend to cancel each other out, leaving you with a much more accurate answer.
You know, when you step back, this whole relay race from AlexNet to ResNet, it's just incredible. It's the story of how we taught machines to see. But this race is far from over. The baton is being passed right now to a new generation of models. And it leaves us with one really exciting question. Now that they can see the world, what are we going to teach them to understand next?